What you see already on this image here is a lovely shot of the Iter complex. We see a lot more pictures later on, and as you can see, it's not finished yet. If you look at my picture behind me, this is how it looks like now. But let's get going. What are we going to do today? I mean, this is, as I said, a virtual visit, but we are, of course, explaining a few background information to you. I'll have a few words about fusion. We talk about what Iter exactly does. I will show you what has happened as of late, and then we take a flight across Iter with a drone, and I will show you also some 360 immersive images, which are really cool, and you get a really good idea of what's going on. And I will switch in the presentation with my colleague Guy, so let's get going. So it's too quick. So, I mean, you are in this area. You're working in this area. You probably know more about this than me, about energy issues. I mean, we have this problem with not the problem, but we can anticipate that in the future we will have a big an increase in demand for energy. The International Energy Agency anticipates that the world demand for electricity will grow by 80% by the year 2040, which is a lot. So all this energy has to come from, and of course we will have to address all the issues. You see some of them here. I mean, we will have the increasing consumption. We want to get rid of fossil fuels. We want to decarbonize society. I guess you're working in the area of renewables, if I understood that right from what Manon said. And the nuclear energy, the traditional nuclear energy, nuclear fission, has an image problem. So a lot of countries are turning their backs on that energy source. I'm from Germany, and my country was doing that already about 10 years ago or something. So another thing is the CO2 capture, which is going to take on, maybe, I don't know whether any one of you is specializing in that area, and that again is also very energy intense. So we have a huge demand in electricity that has to come from somewhere, and we want to make it come also from fusion. We want fusion to provide the base load. Now, fusion as a process, we have an older video where we say, well, the principle is very simple. It's in the sun. We have beautiful sunshine and weather here in the south of France at the moment, so it's warm and bright. All of that comes from fusion. So we want to copy that process on Earth. And how do we want to do that? What you see on the image right now is the Tokamak. This is the device that we are building here at Iter, in which fusion is going to take place. So what you see in the middle, I don't know whether you can actually see my cursor, I'm not sure. What you see in the middle with the light blue indicated there is the plasma, which is sort of going around at half height around the Tokamak. We often call this also a donut, which sometimes I find a little bit of a misnomer, because it's actually more like the inner tube of a tire, because it's kind of hollow, right? And then you have the plasma inside. So what is happening there? This is the reaction that we are going to start within this space that you see there. It's not exactly the same as in the sun. In the sun it's more complicated, it involves more steps, but essentially it's also a reaction between different hydrogen nuclei that fuse into helium. You can see that on the top left. The 2H, that is deuterium, so one proton, one neutron. On the right is an additional neutron that makes it tritium. When they fuse, they create helium, and if you do the math right, you see it's 4 particles, one is left over, and that's a neutron, which carries an enormous amount of energy. This energy would take this neutron, if let loose from here, it would take to the moon only 8 seconds. It would reach the moon in 8 seconds. It's that energetic. So this energy is what we would like to harvest from that reaction here. You can also see that the helium that is released is going to carry some energy, and that as well we would like to use, and I'll come back to this later. Now, of course, there are a number of challenges. I don't know whether you're aware of the temperatures in the sun. For instance, in the center of the sun, we have a temperature of 10 million centigrades. And in order to replicate this fusion reaction on Earth, we need to increase the temperature tenfold. And why is that? Because in the sun, you have a different environment. You have a much higher pressure, you have a much higher density, so you can the temperature there is not as high. I mean, not as high, 10 million centigrades. But we need to increase the temperature here in the Tokamak in order to get to have these hydrogen nuclei fuse. Now, with these temperatures, you can imagine that it's very difficult to actually manage. What kind of material is there that can manage these kind of temperatures? So you might have heard about a magnetic cage. This is what we are trying to build here. So a huge and very powerful magnets will be holding this plasma and shaping this plasma and holding it in a way that it doesn't touch the wall. So that's really quite a challenge, and we get back to this, how we want to do that. Another challenge is to get the burning plasma. So this would be basically like a perpetuum mobile, so that you have an ongoing fusion reaction. This we try to achieve with the helium that we have, that I had mentioned before, the helium as a heating source for the plasma, to keep it inside the plasma, inside the Tokamak, to keep heating the plasma. A word on the plasma. I mean, you are all engineers, you probably all had your physics. I don't think I need to explain it, just a very quick word. Plasma is the fourth state of matter. That is when you heat hydrogen, when you heat a gas so high, so hot, you make it so hot that the atoms basically split into their constituents, so into their nuclei, into their electrons. That's what you then call a plasma. The last of the challenges that are mentioned here is capture the neutrons. We will come back to that as well. This will happen when the neutrons hit the side walls of the Tokamak device itself. As you heard, the atoms will split in their constituents. They will be controlled by the magnets because they're electrically charged, but the neutrons don't carry a charge, so they can escape this magnetic cage. They will hit the walls of the Tokamak, and the walls of the Tokamak will have some material on them that is designed to carry that energy away as heat. So they heat up, and behind these walls you have a system of pipes that carry water at high pressure, so that they can carry off more energy. And then from there on in, it's basically like a normal power plant. It's hot water, it's steam, it's turbines and generators. So why do we want to do fusion? Someone came up with this wonderful phrase, making the case for fusion, and each of the letters stands for something. So fusion is clean because you don't have any CO2 emissions. It's very clean energy. It's abundant because the fuel comes from water. So tritium and deuterium. Deuterium comes from water. Tritium is a little bit more tricky, that we will have to create. But deuterium is abundantly available in the water. Every 6,000th atom in seawater is deuterium. Fusion is safe. Unlike with fission, you just do not have the danger of a chain reaction. We are talking about very light elements as opposed to the heavy elements that you use in fission and you split. We are not splitting anything, we are fusing atoms. And this is actually very, very challenging. And if the environmental conditions are not given, fusion doesn't happen. So basically, if the plasma cannot be kept at the temperature that is needed for fusion, it will just fizzle. There will be no fusion. And there is no danger of a chain reaction. We sometimes get some questions on the safety, in particular in connection with events, like 10 years ago, no more, 20 years ago by now, you remember 9/11. What happens if a plane flies into this? I mean, God forbid, of course, right? Nobody wants to have that, but we need to think about these questions. So you do not have the same environmental impact on the surroundings of a fusion reactor, as you would have with a fission nuclear power plant. What happens is basically that a lot of taxpayers' money is destroyed. There is very little material within the Tokamak that is radioactive. Tritium is radioactive, but it has a half-life of only 12 years. And there's only ever, in this entire Tokamak, and we come to size issues later, there is only ever 2 grams in this Tokamak, in a volume of 1,400 cubic meters. So there is very little of it there. And the 16 years of half-life is also something that can be taken care of in engineering terms. Now, also the side walls that are being bombarded by neutrons will also, exposed to radiation, they will become radioactive, but even that, it takes longer. We think that there will be about 100 years until this material is usable again, but even that, in comparison to radioactive material coming from fission nuclear reactors, this is very little and can be handled. And the E in the case for fusion stands for efficiency. Fusion is incredibly efficient. If you look at that picture, that just gives you an idea. Fusion fuel in the amount of a pineapple, let's say about 750 grams or a kilo, would generate as much electricity as 10,000 tons of coal. So this is quite incredible. And I had mentioned deuterium before. I don't know whether you're aware of a fusion podcast that is run by 5 UK universities by fusion students and plasma experts, plasma physics experts. They have been calculating that a glass of seawater, if you use the deuterium of a glass of seawater, you could generate electricity for one person for over 110 days. Which is quite amazing, I find. But I'm now turning to Guy. He will explain the next question to you, how this will act, what that would mean to you.
Yeah, so I mean, I saw all of these numbers that relate to thousands of tons of coal, but I always found that one very difficult to take into, to evaluate myself and what does that mean for my life. So we did some quick calculations and looked at how much tritium you would need to fuel your entire life. And now this is the primary energy consumption of France. So we took it for France divided by the number of people. So it's primary energy consumption per capita. So it's everything: electricity, heating, transport, industry, everything. And I think, the numbers are spectacular here for me. Does anyone want to give it a guess? Should we open it up?
Anyone?
1 gram.
Ooh.
I don't know. Can you hear me?
I can hear you. That would sound really impressive. So, but that's only a random guess.
1,000 tritium.
1,000 atoms. We need a little bit more than that. I was hoping for an order of magnitude bigger, but anyway, we'll go for it. Okay, so it's 24 grams. It's 24 grams, which is 3 euro coins worth. And that's for your entire life, for a lifetime of 80 years, which I find is absolutely incredible. So that's, I mean, even if you convert that, if you look at the cost of that, it's about 90 euros a year. So I think that really, for me, captures the real incredible efficiency of the reaction. And it's one of the most powerful reactions we know. In the universe, it's where energy comes from in the universe.
Just to give you an idea already of the size of the whole thing, you see a little person on there. I still have to find the trick on using a cursor in this. I guess if I use my cursor, you won't be able to see it. So what you see here is the vacuum vessel of the Tokamak of the entire device. And you see a little person in orange on the right bottom. Okay, that gives you an idea of magnitude. And then think about again what I had said earlier about the amount of fuel, so deuterium and tritium, that we have inside the space there. And you see the figures that I had also mentioned already before, 1,400 cubic meters of the vacuum vessel inside the vessel volume itself, and the plasma volume would be 840 cubic meters. The fuel that you have in there is never going to be more than 2 grams in total. And correct me if I'm wrong, Guy, if the figure that I have there in my head is correct, but I understand that the efficiency of the fusion reaction itself is not actually that high. It's only 0.7% of the fuel will fuse inside the chamber. Now think about that.
But I think the other thing that's worth highlighting is as well. I mean, in a conventional fission reactor, you've got tens of tons of fuel in there, and that really is the risk with a fission reactor. Is you've got all of that potential energy there, but obviously you don't have that in a fusion reactor. You've got 2 grams of fuel in there. That's it. So the reaction stops immediately, and you can't have any catastrophic meltdowns or any incident that uses up that energy in the fuel.
So let's talk about the magnets that I had already mentioned, right? You see this again, and you see again this size comparison. You see a guy in blue next to the whole system. That is the system of superconducting magnets that we need to shape and confine the plasma within the vacuum vessel. So all these magnets are outside, surrounding the vacuum vessel. It's 10,000 tons of superconducting magnets. There are 3 systems of it. You see in the center, the column in the center is the so-called central solenoid that's being manufactured in the United States by General Atomics. Then you see in orange, in the shape of a D, 18 so-called toroidal magnets surrounding the vacuum chamber. And in magenta and dark red, or the magenta are just the clamps, but in dark red, you see 6 horizontal or poloidal magnets that are cut open. And normally at this point I would say, and you will see some later on our tour, so whenever you come here I can show them to you, because they're being manufactured on site due to their sizes. So these magnets, in order to have the strength that they need to control the plasma, need to be cooled down to 269 Kelvin with liquid helium. Right, so this is really quite something, and we will get back to that feature several times over the presentation. What you see next, this item is like a big giant thermos that encapsulates the entire machine. It's the Cryostat. Is one of the largest ones in the world, and apparently it's the largest stainless steel a cryostat that was ever built. It's 30 meters in height, 30 meters across, and it weighs quite a bit, as you can see here. The parts of it were all manufactured in India, and they were shipped here in smaller parts. You see the various levels there. The whole thing consists of 4 parts. There is a bottom part which looks like a soup bowl, and then where you see the round openings, that level and the level below is the lower cylinder, and you see the rectangular openings above. This is the upper cylinder, and you can just make out the lid. We will get back to some pictures on this as well. So these parts were all shipped in smaller pieces here to Iter, and we have a workshop here on site in which a German company, MAN Energy Solutions, was welding this into the big sections, into the big 4 sections. And 2 of those big sections are already in the device in the Tokamak pit, and you see pictures of that in a moment. So how will this work then in the end? You see a picture of like all the elements and components in place here with a cutaway in pink there that is supposed to symbolize the plasma. And by the way, plasma actually does look pink, right, Guy? Well,
yeah. The hydrogen alpha emissions from the plasma give it that characteristic pink tinge.
Yeah,
which you'll see on footage from Jet and other Tokamaks.
Yeah. So there will be a strong current run in the gas in the vacuum chamber to create the plasma. There is continued heating from outside sources. There will be like a giant microwaves or electromagnetic waves, and there will also be a neutral beam that will be shot into the chamber to heat the fuel. And as I said earlier, there will also be heating coming from the helium. That's what we are trying to achieve. Now here I would normally ask a question myself, but as this is a little bit awkward virtually, that doesn't work. It actually always works very nice with French participants in our visits. The whole machine weighs 23,000 tons, so it's not a lightweight, and that's about 3.5 times the Eiffel Tower. So it's quite a bit of weight. So just summing up again, on this part, what we are trying to do here at Iter, we try to show that fusion is scientifically and technologically feasible. So what we are here is a research project. It's a science project. It's one of the biggest science projects running on Earth at the moment. In some of the tasks that we would like to do, as you see below, burning plasma, I had mentioned that, to keep the helium that is created in the reaction inside the chamber, and also to create our own fuel, what we call tritium breeding. Tritium is very rare, but we can create it with lithium if it reacts with the neutrons coming out of the fusion reaction in specifically prepared tiles in the wall. So that will be part of the experiments in the later stage of Iter. And then there is this issue of Q. Q is sort of the efficiency gain of the fusion reaction. What we are trying to do here is we try to get a 10-fold gain, so meaning we want to put in 50 megawatt of heating power to heat the plasma, to get the fusion going, and to get 500 megawatt out. Now, 10-fold, that sounds nice, but it's only a beginning. This is what we do as an experiment, and of course future generation of scientists will have to see to increase that equation, to increase that number 10, to make the fusion reaction also economically feasible. So that is the task of future generations. Let's look at a little bit of history, not too much, but fusion, actually it's interesting, we had an anniversary this year, because 100 years ago, in 1921, Arthur Eddington, a British scientist, first suggested in a public lecture that the fusion reaction is what powers our sun and stars. I'm not sure how much that featured in sort of scientific media, but we saw a little bit on the social media being mentioned on that. And if you're interested, there is a very nice animated video produced by UKAEA that goes on to that story and shows Arthur Eddington and some of the issues about fusion. So we know about fusion since 100 years. And very early on, it was tried already to copy that process, but it was very difficult. Initially, fusion was done in tubes, but the particles were sort of leaving at the ends, and then somebody had a brilliant idea to connect the ends into a torus, and we arrived at the Tokamak. So there is a bit of history even with the Tokamak. It was invented in the then Soviet Union in the 60s, and it's been adopted as a principle or as a device for fusion all over the world. There are over 170 Tokamaks all over the world, and then plus that there are a lot of other fusion devices, because the Tokamak is not the only fusion device. There are others. There is a stellarator in the north of Germany, and there are also more circular fusion devices like MAST in the UK. So this one, what you see here, is next door here in France. That's the former Torres Supra. It's now called WEST, which is at the French Alternative Energy Commission. And then, of course, we come to JET. And now I'll hand over again to Guy. You can take it.
Yeah.
And talk about JET.
So it's worth saying a bit about JET, because actually I think what people may not know about JET is that it actually proved that fusion can generate significant amount of energy. Back in 1997, JET generated 16 megawatts of fusion power. Now that was opposed to 24 megawatts of input, so we haven't reached that Q equals 1 break even at JET. but it demonstrates that you can get significant amounts of power out of the machine. The reason jet is limited in how much it can produce is A, its size, and that's very critical for fusion reactions, but also B, that it's passively cooled, so it doesn't have any active cooling in it. So you're very much limited to the pulse length that you can put into the tiles. And what's going on at the jet at the minute? So jet is playing a really important role at the minute for Iter. So they've installed what they call the Iter-like wall, which is beryllium tiles all over the machine. So actually the machine looks quite a bit different to what you see there. That's the old machine in its carbon configuration. And the beryllium tiles are really critical to ensuring that we have an efficient fusion reaction for many technical reasons. So a jet continues to play that role, that important role, and they're just about to head towards, I think, another tritium experiment, which will validate the design of the tritium walls, and will also provide training for the next generation of operators that will then come to Iter to operate the machine.
Yeah, thank you. Yeah, that is really amazing. And jet here also symbolizes in some ways the incredible international cooperation we have on this entire project. There are so many Tokamaks around the world, and many of them are conducting experiments that are of direct benefit to Iter and the experiments that we will do here at Iter. So it's really an incredible cooperation. Now, this whole issue of creating a fusion reactor goes back to 1985 and was part of the disarmament talks between those two gentlemen, Reagan and Gorbachev. And what you see there, the quote, is a direct quote from the agreement that they actually signed at the time, that they want to develop fusion as an energy source and for the benefit of all mankind. So it goes back quite some time. Since then, the international organization that we now call Iter, which by the way in Latin means the way, has been created in 2006. The agreement was signed in Paris, in the presidential palace in Paris, and it's a very unique project in the way it is being put together. So you see here the 7 member states, so it's 6 countries and the European Union, and among the 6 countries you can see them by their flags. It's the US, it's Russia, it's Korea, it's Japan, India and China. And I'm sure you're curious about the EU, in particular in light of Brexit earlier this year. I can tell you that the EU includes not only the now 27 member states of the EU, but also the UK and Switzerland. And the UK remains in the project because it remains also a member of Euratom, which is the EU body that runs all the business of nuclear energy within the European Union. And there has been an agreement struck on Christmas Eve, actually, on the 24th of December last year, between the EU and the UK to have the UK remain within Euratom. And I just recently saw a nice quote on that, reaction of Ian Chapman, the head of the UK AEA. He said that's like a Christmas present. So the UK remains in the project, which we all welcome very much. Now, a word on the unique formula that I mentioned here. I myself, I have a history, professional history in international organizations like the United Nations or European Union. So what happens there normally is that member states pay their dues, and with those funds, the organizations and the daughter organizations, whatever they are, do their work according to their mission. With this Iter here, it's a little bit different. I mean, the member states also pay their dues, but they pay it a bit differently. They pay between 10 and 20% in cash, while the rest they pay in kind, which means that the fabrication, the building, the manufacturing of the parts for the machine is done by the member states themselves. And you've heard me mentioning some countries along the way when I talked about the central solenoid being manufactured in the US or the cryostat being manufactured in India. You hear more of that along the way. And the good thing about this is that about this type of sharing is that it creates a lot of expertise in all the countries. All the intellectual property is shared between the member states. It's all open and transparent. It does create new industries. I mean, lots of companies have been created in those countries because they are manufacturing first-of-a-kind components, which requires first-of-the-kind industries and companies. And what it also does, it creates a lot of jobs. And finally, and not to be forgotten, it also creates, and what I find very important, it also creates a sense of ownership, which is very important for political buy-in in the respective countries. So it's a very interesting formula. And here you see that the economic benefits are far and wide. I mean, there have been contracts in the value of more than 9.5 billion euros already. And here you get a little bit of an overview. It's only a sample to show you how that looks like when I say the countries are producing or building the machine themselves, fabricating, manufacturing the parts. I will not go through all the detailed items. I can share this with you after this presentation here today, and I will mention it along the next slides. Now, as nice as that sounds to have this international cooperation, there's of course also a huge challenge of integrating everything. The Iter machine consists of millions of parts, so to put this all together in the right time, in the right schedule, in the right way is of course a huge challenge. There have also been, I mean, I'm just mentioning this now in three slides now. Iter doesn't work yet. We have not even finished building the device, but already working on Iter has created a lot of impulse into on innovations. I mean, a lot of new things have come out of Iter as a way of an innovation. We talk here about engineering and innovation. Gyrotrons, who contribute to the heating of the plasma within the vacuum chamber, has got a lot of impulse from Iter, such as vacuum systems. I mean, we have vacuums all over at Iter. I mean, there is a vacuum in the vacuum chamber, clearly by its name, but there's also a vacuum in the cryostat. So vacuum systems and everything that goes with it has received a lot of an impact. I don't know, Guy, whether you want to add anything on the engineering angle of this.
Yeah. I think, so it's worth pointing out, I guess, that the gyrotrons are used for generating microwaves that heat the plasma, and those microwaves, obviously there's many other applications for high power microwaves in very, very, very diverse industries. So that's a real spin-off there that's incredibly useful. I don't know, Kirsten, have you got my slides there, or is it?
They come later. They come
later. Okay.
Yeah. Okay. Mm-hmm.
So we'll talk a bit more about the large.
We come to more. So another one is another innovation that is very crucial here is robotics and remote handling. So. There are two main reasons for it. I mean, one, some of the places where things need to be assembled are difficult to reach. They're very big. It's difficult for people to do that. And then, of course, maintenance. I mean, when inside the vacuum chamber parts need to be exchanged and fixed, I mean, a person cannot go in there due to the radiation. So we need remote handling. That has received a huge impact from Iter. What you see on the right, by the way, is a diverter. This is there are quite a lot of them. I don't have the exact number, Guy. Do you know how many it is? 54 something?
Yes, yeah. I should know that number off the top of my head. Yeah, it's about that sort of
I
number.
should too, and I don't. It's about 50, 55, 54.
Yeah.
And the diverter is kind of the ashtray, the exhaust of the vacuum chamber. This is where the exhaust products are being taken out, and that's it's a particular challenge to build those because there is a lot of there's quite of a heat impact on these parts. So you see this here as well, and the exchange of those parts will have to be done remotely as well. So that's why that example here. Okay, so let's continue. I mean, the machine is not ready yet. We are now at about 72% towards first plasma. The works towards first plasma are done. here a quick overview on how it looks like from now on. We are in 2021. In 2025, we want to launch the first plasma, but you can see already by this graph that we will not have the fusion then. We will start with various steps, different kind of fusion with hydrogen, involving hydrogen, and then deuterium. Finally, in 2035, we will have deuterium-tritium fusion and full fusion power operation. And from then on, we will then see how work continues to achieve eventually a Q equals 10.
So I think it's worth adding there, Kirsten, that the reason for that is control of the plasma is critical to the operation of the machine. So that's why there's a fairly long build up there to fusion power operations. We need to learn how the machine works. We need to develop control strategies for the plasma, and just learning to operate the machine takes that long.
Yeah, thank you. It's quite a big challenge altogether. So it will take its time. Thank you. Here, this is it's sort of like an internal document, basically. Not internal that I can't show it to you, but that just shows you a little bit of what we are dealing with the various different items mentioned here and how this will actually pan out over the next couple of years. You see 25 here, first plasma. This is what we have to all do, and what you will see later is this piece here, this turquoise triangle, is vacuum vessel sector number 6, and that is already here on site, and that's quite exciting, and I'll come to that in a moment itself. So I would like to hand again to Guy, because he was one of the persons who was already here in 2014 and can say something on this comparison.
Yeah. So when I first joined the project, getting on for 10 years ago now, which is even earlier than the photo on the left, we just literally had a brownfield. I think it had just been cleared and levelled, and even in the middle there, we literally just had a hole in the ground. So the progress has been incredible. I mean, it's a shame you can't be here to see it, but the Tokamak building is an absolutely incredible structure, and when you look round the site, and it's very difficult to see from this photo because you don't really get an idea of the scale. It is the amount of work that's been done on this site to build up all of the ancillary equipment is incredible.
We're getting to see this now. We are getting to our picture section. So that's the view that you get from the front. In the front of the structure there is the so-called Tokamak building. In the back, between the two cranes on the right center, that's the assembly hall. And here you have another view, and again, it's really a pity. I have to find out how to work a cursor here to point out some buildings. You see a third from the left. You see the two buildings again. Sort of the lower part is the Tokamak building, the upper part is the assembly hall. North of the assembly hall is the cryostat workshop, where the big thermos, the big cryostat was built. The long building to the right of it is where the horizontal colloidal magnets are being fabricated. Underneath that you have a building where all the cryogenic fluids are being generated, so helium and nitrogen, and then two buildings underneath that look kind of identical. These are the magnet power conversion buildings that will convert the electricity that comes from the right, the grid yard, to the level, to the voltage that we need for the magnets. Thank you, Guy. And on the left, you see later in bigger pictures, that's the cooling plant that we have on site. So let's have a...
If you go back, Kirsten, I'll just point out, right at the top there, top left, you can just see a small ring. And that is the cryostat lower cylinder. So that gives you an idea of the size of the Tokamak relative to the size of the
we see that later a little bit better too. Yeah. So here again in the orange field here is our electrical grid yard and our network. We are connected to the French network. There are two parts of this electrical network. There is a steady state for the plant installation on the right, which is connected since January 2019, and on the left is the pulse power network for the magnets. And this is a view inside one of the magnet power conversion buildings. What you see in yellow there are the giant bus bars. On the outside of these two buildings you have all the transformers and converters coming from China, India, with more equipment also coming from Korea and Russia. And here, this is what you would normally see in person, and this is actually a very interesting picture. This is not the usual photo. In the middle, what you see in the middle is the finished colloidal field coil number 5. It's the second one from the bottom. It's 17 meters large, and it's one of the first ones that will go still this year into the machine. And you see it here basically after it's been completed, after a cold test has run on it and confirmed its functioning under cold conditions. This flat ring on the outside is a so-called double pancake. That's one part of the entire winding pack for a magnet. So you have on the finished one that you see behind, in the center, you have 8 of those so-called double pancakes. So for the next one that is being produced here, you see this part is the colloidal field coil number 3, number 4. That is the third one from the bottom that is being manufactured as we speak. Normally you would actually see that in action, but you can still do that once the situation comes back to normal and we can show it to you. So here you see top view of the building, which we call our cooling tower. It doesn't look like a cooling tower, but it is our cooling tower. Where we have all our cooling water running through from the plant installation, as well as the cooling water from the Tokamak itself. It's quite a giant installation. You see 10 of those funnels on top of the building. In each of the funnels, which is 10 meters wide, you have these kind of rotor blades, these fans. They create an upward drift, and inside of the building, which is essentially hollow, except for some sheets that are in there, that are sort of corrugated plastic sheets that run in a zigzag pattern to create a lot of surface for the water then to evaporate against that airflow that is created by these fans. A very big issue here at Iter is transport, as you can possibly probably imagine. I mean, some of the items, just showing you this one, cannot be transported because they are so huge. They have to be manufactured on site. And you remember me saying that also of the cryostat, it's so big you cannot transport it, you have to manufacture it on site. But even the parts that can be transported are huge. I mean, they're usually up to 10 meters wide. What you see here is one of the D-shaped toroidal field coils crossing a highway. It's the highway that we use, a lot of our colleagues use to come to work, and we always see the signs along the highway that it's being closed at night every so often. And that is because this happens, because these items are coming along the so-called Iter itinerary, which is a roughly 100-kilometer route along which the items are being brought from the port near Marseille, Fos-sur-Mer, and then along this itinerary to Iter. This is a very nice atmospheric picture. What you see in the back is the smallest, one of the smallest of our colloidal field coils at 10 meters. It's the lowest one. That is the one that goes first into the Tokamak very soon, actually. PF6, this was manufactured in China for the European Union. When I'm saying that, it goes back to the way our project is organized. So Europe is responsible for colloidal field coils numbers 2 to 6, but because in the building where they manufacture them, you can only produce one size magnet at a time. This one was outsourced to China and then was brought here, so that was last year, as you can see by the date. Now this was something really spectacular, and if you want to see more of that, go to our website. We have a video of showing you the insertion of this giant piece. That is the base section of the cryostat. This is our single most heavy item that we had to move at 1,250 tons. And for the movement of this item, we had to also reinforce the surface on the outside, where you see this vehicle standing there. That surface has been reinforced about 2 years ago to allow the transport of this kind of item across into the building, as you can see it. So the viewpoint that we have here is basically from the manufacturing workshop where it was put together, and what you see there in front of us is the so-called cleaning building, where all components are being cleaned before they are being put into the assembly hall. And that's what we see next. And I don't know what you think about this, but I think that looks pretty much like a science fiction movie. You could easily label that as done by Steven Spielberg, if you ask me. I mean, that looks like what is the movie called? The Encounter of the
Close
Third
Encounters
Kind?
of the Third Kind.
That's the one. I think that's totally that. So this was a spectacular operation, and in a moment, a guy will tell you more about the challenges of that. I will actually leave it to him. Just one more picture on this. What you see here is the second item that has already been moved into the Tokamak pit. That is the cryostat lower cylinder that was put on top of the previous item here. And I'll pass the floor now to Guy, who will tell you a little bit more of the challenges attached to that.
Yeah, so I think one of the things I wanted to do in this lecture was give you some of my perspective of some of the real challenges on the project. And I think one of the main ones we've got is metrology. So again, I'll open it up for audience participation. So can you give me an idea of what you think is one of the most precisely made machines, mass-produced machines that we have? You know, that the common person would imagine is a highly accurate machine. The clue's on the right.
Anybody?
So we'll go for it.
Swiss watch.
Yeah, okay.
Yeah.
That's what I was hoping you'd say. Okay, so Swiss watch. Okay, so I used to work with components made for Swiss watches, made with a similar sort of company. And so if you look at the characteristic size, they were of the order of 1 millimeter, and tolerance, well, if you were lucky, you'd get to 1 micron. So we've got a precision ratio of about 1 to 1,000. Then we look at the Iter TF core. So it's 17 meters roughly in size, and we've got a tolerance of 2 millimeters on that component. So about 8.5 times harder than the Swiss watch. And this precision is absolutely critical to harness the force of Iter. There's huge forces generated in the magnet system, and there's huge forces that come from the plasma, and for things like plasma disruptions, which we can discuss later on. And so one of the real elements, or why we can build this machine now, is down to large volume metrology, and we use them non-stop. So we use a couple of different methods, but the main one is probably the laser tracker. And again, this gives you very accurate measurements over large volumes. So on the left, well, sort of in the middle there on the top, you can see a typical laser tracker that we use. On the top right, you can see a Leica T probe. So that's something that we can use to very precisely position components. So again, it's not just measuring where components are; it's also measuring where they're installed. Down at the bottom right, you can see photogrammetry system, and that's an alternative to laser trackers. That's a bit more flexible. And down at in the bottom center is a laser templating system that we've just started using. Related to that, and on a more technical side, is the management of the data from all of these measurements and all of this CAD data, and that's again has been a real challenge to get right through the production phases. I'll just talk a little bit more about the laser templating, because this is one of my particular interests. So this was brought in to allow us to position components. So we've got about 150,000 components to position on the vacuum vessel, and if you can imagine, that you can't do that with conventional markings, you can't measure it with measuring tape. We also need to be incredibly accurate. So we took this system from a company in Germany and put it into service. And so this is a real application of the latest technology that's available in the marketplace that we've used on the machine to improve efficiency and to meet the accuracy requirements.
Thank you, great. We are back to some nice photos again too, just to illustrate all of that. What you see here is an inside view of the Cryostat workshop, and what you see is all the lid sections having arrived at Iter, ready for assembly in the Cryostat workshop. And what I said before with the transport, this is the size of the parts as they can actually be delivered to Iter. So they're already rather large. I mean, mind you, the convoys that are coming here, they're always exceptional load convoys, I mean, in terms of weight and in terms of dimension. So even the parts, when they come in, this is all very big. So, and this is how it looks like now, and what I present to you right now is actually an artistic rendition of the lid as it is being assembled. The photo is by Christian Lünich, a German photographer who uses some kind of special technique applied on his photos. He is an award-winning photographer who has accompanied Iter since quite some time already now. Currently, one of his photos is part of a big project that has gone around the world already as a photo exhibition. It's called Civilization. It's currently on exhibition in Marseille in the Moussa Museum. So he's been here last week actually, and this photo is really, really absolutely new. This was made last week only. So this goes a little back. This is in July last year, where we celebrated symbolically the start of assembly. The start of assembly was a bit before that, but we had a big ceremony in the assembly hall, and you will see later pictures of the assembly hall. It doesn't look like this anymore. It's a lot fuller and packed right now. But we had the privilege of welcoming a number of heads of states, among them not in person but virtually. Among them President Macron of France, and a lot of other dignitaries to mark the actual start of assembly, which was a huge milestone for all of us here.
Is it worth, Kirsten, maybe saying a bit about what you can see in that photo? So,
I come to that. I have pictures of that later. Yeah. But maybe we can use it already now. So what you can see on this is here in the back, and you see later a better picture of it. These are our sub-assembly tools. These are two giant tools that have been manufactured in Korea. They're also first of its kind tools. They are there to put together the vacuum vessel sectors. There are 9 of those. With the accompanying 2 toroidal field coils. You remember the D-shaped ones, and thermal shielding. I have pictures of that in action in a moment. You see on the right this structure on the middle right, sort of lying down, a big steel structure. That's a so-called upending tool, and that has actually come into play these days. Unfortunately, I didn't have time to add the photo where the first vacuum vessel sector was actually lifted, but you find these images on our website. So here is the first vacuum vessel sector in the assembly hall, and you can see behind it on the top again the upending tool. We are looking at the assembly hall now from a different angle, and on the right you see some of the columns of the subsector assembly tools. So these parts were manufactured in Korea by this one particular by Hyundai Heavy Industries. Some of them are also manufactured by Europe. Oh, this is you again.
Okay, yeah. So again, my particular area. So I'm involved in the in-vessel area. So again, what I wanted to talk about was the particular challenge of how we maintain configuration control. So as I said earlier, I think we've got about 150,000 attachments that are welded to the vacuum vessel. And the problem is we don't have any space left. The vacuum vessel is huge, but we don't have any space left in it. So the tolerances are down to millimeters. And you can imagine we've got people from all over the world that are designing all of these systems concurrently. Suddenly they need to adapt to, a new requirement, and they need to move, or they need to change the number of supports, and this has a huge knock-on effect for the rest of the system. So again, one of the real enabling technologies for this machine, and that I'm sure will relate to you, is 3D modeling and how we control that data, but also how we integrate metadata in with the 3D model, and especially things like scheduling. So we're using 4D scheduling technologies, and also looking at tolerance analysis, how you use those models in a practical way, and how you arrange them for tolerance analysis. So I think that's been one of the real enabling technologies for this machine.
Great, thank you. Just a few more pictures, and then I will show you the drone video, which also gives you a much better idea of how things look like here. What you see here, which looks actually transparent, is a part of the thermal shield for the vacuum vessel. The thermal shield will be surrounded by vacuum shielding because of the magnets. You have to imagine that within the machine itself, you remember the temperatures. You have a plasma of up to 150 million centigrades, but the magnets need to be cooled to 269 degrees. So the thermal shields are absolutely essential for this gradient that is absolutely unique. It will be absolutely unique in the universe.
Yeah, it's over about a meter. You've got that temperature change.
Imagine, yeah, it's quite something. So here you see it, and you see the two parts of the of one side of the thermal shielding. In one of the subsector assembly tools, they've done some test operations there. And this is also from last week, and ahead of the lift of the first vacuum vessel sector into a vertical position, a photo by our photographer, by the photographer Christian Unit. Here's a nice picture also from the top into the assembly hall. You see it looks quite different now. Some interesting parts on the left top. You see the subsector assembly tools coming down. On the left there is a circular structure like a column. That column is the bottom part of the in-pit assembly tool central column. You have to imagine that when we put the vacuum vessel sectors into the Tokamak pit, they have to be supported. They cannot be freestanding. And we have a particular tool for that. It's called the in-pit assembly tool. It's like a giant umbrella, which consists of a central column, of which the first part you see on the left. It has since, this is also last week, by the way, since then it's been moved into the Tokamak pit. And then you have radial beams that will support the upright vacuum vessel sectors until they're actually being welded together and until the support is no longer necessary.
And you can see that radial beam there on the red structure.
That's it, yeah. So we are almost done. This is a peek into the Tokamak pit itself. That's quite old, that picture. That is from last year when the temporary lid was removed. But I wanted to show you that to have this top view, because at the moment this is no longer possible except for the drone, which you will see in a moment. And this is one of the latest pictures. It's not really totally updated because so many things have even happened over the weekend. But what I want to show you next is the drone video, and I hope that you have everything sound and image. So here we go, a flight across Iter.